assumptions. This is a good example. It's about a completely randomized design. Essentially, the design is the extension of the t-test for comparing two treatments. So at the end of this chapter, when I'm showing you the concept map, I will categorize all of these different like t-test, f-test. I will tell you that where to use it for each of them. So here is that t-test when we want to compare two treatments to the comparison of k treatments which have between like random and allocated. So here is an example. Look at here. I have a table with different diets, like I would say A, B, C, D, and then I'm going to measure something. That's like this. So I'm going to have like, let's say animals. I'm going to get their blood drawn from 24 animals, randomly allocated to 4 different diets. And then I would say that, and the reference is Bucks and Hunter. So the diets, I would call them A, B, C, D. And that's the observation, like when I got the, I did the blood test. So this is the observation, like the data that I would have. And let's say it's in time. So it's going to be in second, for example, the unit is second. So that's allocated randomly, blood samples taken and tests randomly. So random, we don't have any problem with the randomization. It's a completely randomized experiment here. Yeah. So here we would say K. In some books they call it K. In some books they call it T. So I'm gonna tell you, like, we want to know both of them, but know that it's like the number of the treatments that we have. So I would say I have 4 treatments, and for each of these treatments I have the number of the data points. So for treatment number 1, we have 4 data points. You can see like 62, 60, 63, 59. For the treatment number 2, I have 6 data points, which is B. For treatment number 3, which is C here, I have 6 data points, and again for treatment number, it's just randomly, it's just numbers. For treatment number 4, which is like D, diet D, I have like 8 data points. So N4 is going to be equal to 8. And the treatment totals is like just add them, and then you can get the average of each of these treatment as well. For example, you can say 244 divided by 4 is going to give you the average of treatment, like what's happening inside treatment A or inside treatment B. Then you get the average for treatment B, C, D as well. Also, we can have a grand total. And grand total means that you're going to add all of these together, and you can have the grand total average as well, which is going to be 1536 divided by the total number of the observation that you have. You would divide it by that, like 4 plus 6 plus 6 plus 8, and then like 24, right? And at the beginning, you said we have 24 animals, but you can add them as well. So we say 1536 divided by 24 is going to give you total, grand total average. So it's like all the diets, all the treatments together. And we can look at, show it on the figure, like we would have it like this. It's the plot measures responses versus treatment. Here is responses as time, we said, and this is the diet. So it's like you can look at it, that you will see that diet A, B, C, D, the treatment that they have is like the response that they have is different. Okay, look at here. For the same example that I said, we would say it's assumed that the effect model for this design is that this is a general equation that we have for the effect model. We would say YTI is equal to the like mu, which is the mu is the overall mean, plus tau T plus epsilon of the TI. Tau is like the mu of the treatments, like each of those treatments. We said that we have, for example, in the previous example, we had 4 treatments. So each of those treatments, they're going to have their own mean. So the mean of these treatments minus the overall mean. So the deviation of treatment mean from overall mean. The epsilon, we call it error. So epsilon means very small number. Like here we would say the epsilon is like the error for the ith observation n of the like the number t treatment, like the treatment that we would have. And we would say for the error, we have the normal, and this ID like sigma, sorry, 0 and sigma 2. It's like that. We would say it has the normal independent distribution, and then this I means independent distribution. The mean is sigma, sorry, the mean is 0. The expected value for epsilon is 0, and the variance is going to be sigma 2. So, but the question that we have here is that, are there any real difference between the diets, between these treatments that we would have? So what we are trying to determine is that is the variation between treatments means significantly larger than the variation that occur within treatments, like the inside the treatments. So the variation that you would have between like treatment A, like diet A and B, the variation between these two are like significantly larger than the variation that is going to happen like inside like A or inside B. And when you want to write it, when we want to find it, we would need to define hypothesis test as the null and alternative. So the null hypothesis, we would say the tau of t, which is the deviation of treatment mean from overall mean, is equal to 0 for all k treatments. And then we're going to define the hypothesis and would go with the test statistic. We're going to work on examples on it. So here is like, let's expand whatever we had on the, like, remember we had the different sum of squares. We would say we have sum of square of regression, sum of square of the error, and those ones. That one was when we were talking about the like linear, for example, regression models. So here we want to talk about the sum of the squares when we have the within treatment and like between treatments. So the first thing is total sum of a square, SST, or you can write it like simply S. The total sum of a square, in some books they call it total corrected sum of the squares because it has a correction factor for mean. So when we say total sum of a square, it's like the total of the observation, the sum of the square of the observation. Look at here in the example that we had. So it's like 62 square plus 60 square. So all of them you're going to score it. All the individual, like for example, we had 24 observations, so we would square them. And even when you look at here, it's written treatment number like 1 to K. So we have 4 treatments. It's going to be 1 to 4. And then I is equal to 1 to N, but for that specific treatment. It's like that. We would say, for example, for the first diet, first treatment, like K equal to 1, we had 4 N, like 4 observations. We had N was 4, in fact, for the other ones. So it's like that. You would say that, okay, I'm going to square all of these individual observations and then add them. And then we have correction for mean. For the correction for mean, it's 1 over like whatever total number of the data point that we have, which is 24. And then here it's like it's going to give you the grand total, like sigma by TI power 2. So what's the difference between this grand total, this part, and this part is that here you would square individual observations and then add them. But in the correction for mean, you add them first and then square them. I saw that over time, like students, they do this mistake when they want to calculate DS total, so they consider both of them the same. And please be careful, don't do that. And then here we find out the total sum of a square or total corrected sum of a square, as I said. They call it both like as 340. For the degree of freedom, we would say we had 24 data points, minus 1 is going to give us 23 degree of freedom. So the formula we use above, and it's like that. You can compare the formula that we have here with the formula that we had in the chapter 1 and chapter 2 when we were talking about the sum of a square. They're very similar. And the only difference is that here we are talking about the corrected sum of the square. Okay, so now that was total sum of a square, like for the total, like corrected sum of a square, but we are talking about the total observation. Now let's talk about the what's going to happen between treatment and within treatment. So for the between treatment, as I said, is like that. We had like 4 different, for example, in the problem that we had 4 different diets. So what's going to happen between these diets is going to be between treatment. And we want to calculate the sum of a square of it. So it's like that. I would say take t equal to 1 to k, like k is 4, right? And then I would have the number of the treatment that I have times like y bar t minus y bar, and y bar means that the mean for that one, and a square of it. We can expand it mathematically, and then we would have this equation. It's very similar to the total sum of a square that we had, but here we are talking about just the treatment, like among the two, like between the treatments, what's going to happen. And here we would say, okay, so sigma t equal to 1 to k, treatment totals. So for each of those treatments, we had the totals, right? So it's like that. I would get the treatment totals like individually and then square them. Let me go back and show you what do I mean by that. Look at here, for example, 244. This is the one column, like one treatment. So it's going to be 244 square plus 396 square. You see what I mean? It's like that. Each of these columns, you are going to square it. Then we are talking about the, because we don't care what's happening inside them. And when we are talking about the between treatments. So let's go back to the between treatments. It's like that. All of those, when you add them, like we would have the with a square, like you would say the first column, whatever you had as a sum of the first column, power 2, divided by the number of the treatment. Like for example, the first column, that A, it had 4 data points, so divided by 4. And then you would say that plus the second, you would do the same things for the diet B and diet C and diet D. And then you would say minus correction for mean. So for the correction for mean, you have the, look at here. So you have YTI, and then T equal to 1K, I equal to 1 to the number of the treatment, which is going to be 98,304. Look at here. So the correction for mean, the value that we have for the total sum of a square, like total corrected sum of the squares, it's the same correction of mean that we would use here. And equal to, like we would get 228, but the degree of freedom for between treatments is like that. We have 4 treatments minus 1 is going to be 3. So within treatments is a little different. We're talking about the, we are interested, we're talking about what's happening inside each of these treatments. And we would show it by sum of a square of the W. As I said, you can write down SW or you can write down SW. Both of them, it would represent like the sum of the squares. And then for the within treatments, we would say, okay, so let's say the bigger sigma is like going to be T equal to 1 to K, and the smaller sigma, like inside that, is going to be I equal to 1 to N for each of those because we said that we're interested what's happening inside each of these treatments. So here is that what's happening inside the treatment. And then we would say YTI minus Y bar of that specific treatment, power 2. Or we can write it down like playing with it a little, and then it's going to be equal to S total minus SB. It's like that. Whatever sum of a square of total that you had minus the sum of a square of the between treatments. And so when you think about it, even before we had it like this, we said that, for example, sum of a square of the total is equal to sum of a square of the regressions plus sum of a square of the residual, right? So here, sum of a square of total is going to be equal to the sum of a square of the between treatments plus sum of a square of the within treatments. So that's going to give me the sum of a square of the total, or total correct sum of a square. And then we would say, so here we found that, for example, the first one was 340 minus 228 to the 112. If you do the calculation for each of them, like inside them, you're going to get the same answer as well. If you don't want to do this deviation. The degree of freedom for it, we have this rule. You can say sigma t equal to 1 to k, nt minus 1. And then it's like that. I would say, for example, the first diet A, I had 4, right? So what's the degree of freedom for the first treatment or first diet? 3. So I would set aside this 3 plus. For second diet, I had 4 again. 4 minus 1, it will be 3 again. So I would put this 3 added to that, the first 3 that I found. And then I had 6 treatments for that number, like the third diet, treatment number 3, diet C. So it would be 5, the degree of freedom for it. And then the last one, I had 8 diet, if I'm not wrong. And then we would have 7. So you would say 3 plus 3 plus 5 plus 7. And you would get the, or you can say that, okay, so let's say degree of freedom of total minus degree of freedom that I would have for the between treatments. So it would give me the degree of freedom that I have for error. So you can do both of them. So here, that is between treatments. It would be 3. Sum of a square is like 228. And then for within treatments, degree of freedom is 20, sum of square is 12. So you can switch these 2 columns as well. We call it ANOVA Table for the between treatments and within treatments. And we can find out mean square, and then we find out the F value for it. It's very interesting when you look at it. It's very, so if we know the concept of the ANOVA Table, if you just have it in your brain that, okay, I have the source of variation, and then I would have the sum of a square, degree of freedom, mean square, and F value. So here it's the same. So I have the degree of freedom, just switch the columns, that's fine. You can write down sum of a square first. Sum of a square, degree of freedom, and then the mean square, which is like sum of a square divided by the degree of freedom. And like before, that we had this within treatments like error, MS of this error is going to be the same as the sigma 2 that we have. So we can, but if you were looking for the variance of the whole system, it's going to be 5.6.